quality of life depends on energy. And yet energy is one of the greatest challenges we face. We need cleaner, more efficient, and more reliable energy than any other source. To make that a reality, we are creating a sun here on planet Earth. My name is Alain Bécoulet. I am the chief scientist of the ITER organization. ITER is a scientific project that is aiming at reproducing nuclear fusion reactions as a new energy source. In today's nuclear fission energy, the nuclei of an atom is split into two nuclei. And fusion is the other, let's say, side of the nuclear physics. You can extract energy not only from breaking big nuclei, but also from joining, from merging small nuclei. But that requires the kind of conditions that you have in a star. The basic concept of a tokamak fusion reactor is to create a spinning plasma by accelerating and compressing hydrogen isotopes with large magnets around a circular donut shape. This mixture has to be raised to a very, very high temperature. When I mean very, very high, is 100 to 150 million degrees, which is hotter than the core of the sun. In these conditions, the nuclei in the plasma begin colliding and form heavier nuclei, which releases huge amounts of energy. It's not a chain reaction. It cannot go out of control. And nuclear waste is minimal. Fusion is the most condensed source of energy that physics allows us to access. If I extract elements from your laptop battery and your bath this morning, I can generate enough energy for your entire life. It is a huge scientific and technological challenge. A fusion reactor must be extremely precise. Management, monitoring of the assembly is key to the success.
We're working with hundreds of meters down to a tenth of a millimeter. We've got a platform, the work site, which is 1 kilometre long by half a kilometre wide. The machine is 23,000 tons, 28 metre diameter, 29 metres tall. The alignment for the magnets is 1 millimetre. The interfacing where we're joining the conductors together is 100 microns.
Metrology is a science of measuring with high accuracy in 3D. So all our components are coming from our member states with a key characteristic. It would be impossible to construct ITER without extremely precise metrology. So it is applied from the supply chain, from the manufacturing point of view, to the assembly, to the very end of the tokamak until the last element is actually inserted.
Hexagon is our preferred supplier for metrology equipment. With their great support and vast amount of capability, they supply pretty much all of the metrology equipment that we utilise on the site.
The Hexagon metrology equipment we use range from probing systems to scanning devices on the large volume side and handheld scanners for more close-up areas of the components. The use of the Hexagon instruments is combined with the use as well of the Hexagon software. So we acquire real measurement of as-built components, then do a virtual fitting to compare with the CAD files in a kind of hybrid model. This data is then combined with the supplier data under one reference. This set of data helps us to identify any deviations, repairs, clashes, collision risk, or potentially to not being able to assemble as designed. It saves both cost and time, so it is key to the success of the project.
Quality is not simply a nice to have, it's absolutely a must have.
A measurement that you cannot qualify is no measurement at all.
Precision and quality is instrumental to achieve similar to the sun conditions.
ITER will reach its operation point goal when we reach what we call the steady state. This is to be reached in the second half of the next decade. This will be the integrated demonstration that we have succeeded. Clearly, we believe that we will see fusion energy being deployed around the world during this century. This will give access to the worldwide population to a better energy for the quality of their life.